Hello, in this video I'm going to cover section 9.5, Measuring Temperature from Contemporary Mathematics by OpenStax. The learning objectives of this section are to convert between Fahrenheit and Celsius, identify reasonable values for temperature applications, and solve application problems involving temperature. So when you touch something and it feels warm or cold, what that's really telling you about the substance is its temperature. So temperature is a measure of how fast atoms and molecules are moving in a substance, whether that be in the air, a stove, or in a cube of ice. So the faster those atom molecules move, the higher the temperature. So in the metric system, measurement of temperature is measured in Celsius scale. They actually have a second scale in the metric system called the Kelvin scale. We're not going to talk about that in this particular section or book, but they do have a second temperature that is standardized. And so Celsius is the one we're going to focus on between Celsius and Fahrenheit. So because temperature is a condition of which the physical properties of a substance, the Celsius scale was created with 100 degrees separating the point at which water freezes and the point at which water boils. So in Celsius, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. And that just kind of gives us this nice standardization of temperature. So scientifically, these are the points at which molecules change from one state of matter to another. So like going from ice, where it was frozen, to a liquid, and that's from 0 to 100, and then at 100, water will turn to a gas, or as we know, water vapors. And watching a water boil on the stove, if you take it from frozen up to boiling, you can watch all of these stages occur. So this figure here lists some common temperatures on both of the scales, so we kind of have an idea in comparison. Since we in the US don't use Celsius daily, it's oftentimes difficult for us to really know and have an idea of what that means. Luckily we don't have to. We're very much in the Fahrenheit system, and we kind of we have a really good understanding of what Fahrenheit is and what it feels like. But we can convert between the two, is what we're going to do in just a moment. So I want to talk about some things here in this figure. Let me grab like a little laser pointer. So here, the idea of absolute zero. You might not have heard about this, but absolute zero is negative 273 degrees Celsius, or negative 459 degrees Fahrenheit. And what this is absolute zero is where atoms no longer move whatsoever. Atoms are completely frozen in place. There is no atomic movement at absolute zero. And so that is way, way cold, right? That is way, way cold. Absolute zero. So helium, which is a gas that's in our atmosphere, it will boil at negative 452, which is pretty interesting, which means that below negative 452 degrees Fahrenheit, again, really cold, helium will be solid, which is pretty crazy. And then we jump all the way to 32 degrees Fahrenheit. So 32 degrees Fahrenheit. And that's when water freezes in Fahrenheit, and that corresponds to 0 degrees Celsius, and that's when water freezes in Celsius. So like room temperature, just kind of interesting, we consider room temperature in the Fahrenheit system to be 72. That corresponds to 22 in Celsius. Or a fever of 104 is 40 degrees Celsius. And then going like up to an oven, like 450 is 232 degrees Celsius. And then again, water boils at 212 and 100 Fahrenheit and Celsius respectively. And so again, 32, 0, 212, 100, that's our two major points. water freezes, water boils. That's our two major pivotal points in these two systems. So how do we convert between these two systems? Well, we have these two mathematical formulas, and this says to get Celsius, we plug in Fahrenheit, we subtract 32 from that Fahrenheit temperature, multiply it by 5, and then divide it by 9. So 9/5 times the difference of Fahrenheit and 32 will give you Celsius. And then to go to Fahrenheit, you kind of work in the opposite direction. You take the Celsius temperature, multiply it by 9, divide it by 5, and then add 32. So this is called an inverse operation when they're kind of opposite looking of each other. So these are the formulas for converting from Fahrenheit to Celsius and Celsius to Fahrenheit. So where do we get those formulas from? I think that's kind of an interesting question, like where did they come from? And I wanted to talk about that because it actually comes from a bit of algebra. So I am going to do a little bit of algebra here, but not enough to hopefully scare you away. So let's talk about water freezing. So here we have a point, right? We have a point. And that point is 32 and 0. So what we're doing is we're taking in 32 degrees Fahrenheit and popping out 0 degrees Celsius. And then another point we have is 212 and 100. So what we're doing here is we're taking in 212 degrees Fahrenheit and we're outputting 100. So how can we create a relationship between these 2 points? Well, we can create a line. So the equation of a line needs 2 things. It needs a point, which we have 2 of. I'm going to pick the point 32 and 0, and it needs a slope. So lines have slope. And just to remind you what slope is the difference in the y's. So often we write this as y2 minus y1 over x2 minus x1. So it's the difference in the y's divided by the difference in the x's. So in this case, the y values are the outputs, and then that should be a 2. And then the x values are the inputs, so x1, x2. So if we plug those values in, y2 is 100 minus, let me make that a little bigger. So y2 is 100, y1 is 0, and then x2 is 212 minus 32. So if we were to simplify that, 100, that's going to give us 100 divided by, and then 212 minus 32 is 180. And then if we simplified that again, that would give us 5 over 9. These are both divisible by, they're both divisible by 10 and then 2, so they're both divisible by 20. 180 divided by 20 is 9. So reducing that gives us 5/9. So that's our slope. That's that 5/9 that we talked about, because what we're doing again, we're plugging in Fahrenheit and getting out Celsius. Right? We're plugging in Fahrenheit and getting out Celsius. So that was that 5/9 in the Celsius equation. And so then we use what's called the equation of a line, right? Which was y equals mx plus b. Well, in this case, we have a y value. We need to pick a point. I'm going to pick this point because it's 0, right? It has anything that, when you're picking points, if it's got a 0 in it, that tends to work out pretty nice. So y is 0, the slope is 5/9, x is 32, and we've got plus b. End up that being 0 equals 160 over 9 plus b. So b is negative 160 divided by 9. So let's kind of look at what we've got here. We've got y equals 5/9 x minus 160 divided by 9. They both have 9s on the bottom, so if we factor out, actually I can factor out a 5/9, and that's going to give me x minus, and then 160 divided by 5, because we pulled 5 out of it, is 32, and we pulled that 9 out of both as well. So because this y really represented Celsius, if I can make that a C, that's 5/9, and because x really represented Fahrenheit, I can make that an F. That gives us our formula that we had on the previous page to go from Fahrenheit to Celsius. And so if we wanted to then have the other formula that takes us from Celsius to Fahrenheit, then we could solve for F by multiplying both sides by 9/5, because that's going to get rid of that fraction. We're multiplying by the reciprocal. So 9/5 times Celsius and then add 32, that gives us our other formula. So these formulas just come from a little bit of algebra there that we can implement to solve these problems. So I wanted to just talk about that because I think it's nice for some students to know, because they're interested, like, where do these formulas come from? And it comes from this little bit of algebra. Alright, so here's an example converting from Fahrenheit to Celsius. A recipe calls for the oven to be set to 392 degrees Fahrenheit. What is the temperature in Celsius? So again, thinking about our formulas to go from Fahrenheit to Celsius, if we want to go back. So we're plugging in Fahrenheit and we're getting out Celsius. So that's going to be the formula C equals 5/9 F minus 32. And so we're going to say the Celsius temperature is 5/9 divided by 392 minus 32. And using our order of operations, we do the inside first. So we're going to do 392 minus 32. We're going to multiply that by 5 and then divide it by 9. So that's going to be 200 degrees Celsius for that oven. So this is kind of interesting, a lot of times you hear, Fahrenheit and Celsius, and you're just like, well, what's a quick way to do that? Like, what's just something off the top of my head? And so this is kind of a way to kind of do it off the top of your head. It's if you're going from Fahrenheit to Celsius, subtract 30 and half it, instead of having to like do the 5/9 or the 9/5. We can just do a factor of 2, because 9/5 is almost 2. It's just under 2. It's about 1.8. So if we were to, scale the 32 back to 30 and then divide by 2, that kind of fixes the math a little to get us closer to what we want. So this is a good way to estimate off the top of your head one to the other in this case. So the book mentions this, and I just think it's a neat little trick to use when you're just trying to estimate off the top of your head. This doesn't give you the exact value. This is an estimate, all right, or a reasonable value. This is just an estimate. So, for example, if you had something like this, what's a reasonable value, and you didn't want to like pull out a calculator, then what you would do is we have 5 degrees Celsius. So if we wanted to convert that to Fahrenheit real fast in our brain, what we could do is we could double it and add 30. So that's going to be 10 and 35 degrees Celsius or Fahrenheit. So this is about 35 degrees Fahrenheit, as where this one is, if we double this is going to be about 20 degrees Fahrenheit. So doubling this is negative 10, and adding 30 is going to be about negative 20. So which is more reasonable for a freezer? Well, definitely negative 5. We want to be below freezing, so negative 5. Another way you could have answered this question, what's a more reasonable value for a freezer? Well, you want to be below 0, right? And remember, in Celsius, 0 degrees Celsius is freezing. So that's when water freezes. So that would be our pick. So B is more reasonable for a temperature of a freezer. All right, let's look at one last example. The optimum temperature for a chemical compound to develop its unique properties is 392 degrees Fahrenheit, pretty hot. When the heating process begins, the temperature of the compound is 20 degrees Celsius. For safety purposes, the compound can only be heated 9 degrees Celsius every 15 minutes. So how long until the compound reaches its optimum temperature? So two ways we could do this. We need to be in the same units. We cannot be in two different units and do math with them. So we need to convert to one unit of measure. So what I would advise is, since everything else except this is in Celsius, let's convert 392 degrees Fahrenheit to Celsius. So that's going to be 5/9 times 392 minus 32 to get that over into a degree Celsius. So that's going to be 392 minus 32 times 5 divided by 9. And that's going to give us 200 degrees Celsius. So we're trying to get this thing warmed up to 200 degrees Celsius. It begins at 20 degrees Celsius, and we can only heat it 9 degrees every 15 minutes. So how are we going to kind of reason through this problem? So first of all, how much of a difference in temperature does it have to go? Well, so the difference in temperature is going to be 200 minus 20. That's in degrees Celsius. So we're looking at 180 degrees Celsius difference. And we can only go up 9 degrees every 15 minutes. So 9 degrees Celsius every 15 minutes. So if we divided by 9, so then if we say, well, how many intervals of 9 degrees do we have? So how many intervals of 9 degrees are there? Well, that would be 180 degrees Celsius divided by 9 degrees Celsius. And so what that's telling us is 20. So this is 20 intervals of 9 degrees Celsius, and that happens every so this 20 means we're gonna increase by 9 degrees Celsius 20 times. All right, and so that's going to happen every 15 minutes. So then the total time is going to be 15 minutes times the 20 intervals of 9 degrees Celsius. So that ends up giving us 300 minutes. All right. And we can convert that into hours. If we do 300 divided by 60, then that is 5 hours. So it's going to take quite a while to get that nice and warmed up. All right, one more example. An 8,000 BTU air conditioner can cool a room 1 degree Celsius every 5 minutes. If the temperature is 24 degrees Celsius, how long will it take the air conditioner to cool the room to 20 degrees Celsius? So this time it's nice. It's got everything in just degrees Celsius. So what we're trying to do is cool the room just 4 degrees Celsius. And it can do that every 5 minutes. So 1 degree Celsius every 5 minutes. So that would take 4 intervals, right? Because it's going to go 1, 2, 3, 4 to get to down, and that's going to be 5. So all that is 4 degrees Celsius per minute times 5 minutes, and that's going to be 20. So it should take about 20 minutes in order to cool that. So let's look at this. This is our last example. So we've got an 8,000 BTU air conditioner. It can cool a room 1 degree Celsius every 5 minutes. The room is currently 24 degrees Celsius, and we want it to get it down to 20 degrees Celsius, which again is about room temperature. So we want to go down 4 degrees. So if we do 24 minus 20, that's 4 degrees Celsius difference. And it can go 1 degree Celsius every 5 minutes. So we've got 4 intervals of 5 minutes and times 5. So that means it's going to take about 20 minutes to get it down with an 8,000 BTU air conditioner. So that's just that was really it. That was a quick calculation just to kind of show you that if everything's in the same units, it works out nicely. It's only in the last problem where we had that 392 degrees Fahrenheit compared to all the other Celsius that we need to do a conversion. But again, this is about room temperature. So all right, so that is it for this video. If you haven't done so already, I highly advise you take the time to read section 9.5 in the textbook. There are throughout the chapter problems called Your Turn problems where you get to practice and check your understanding. So I would advise you do that. And once you're done, head on over to the LMS and complete the online homework assignments.